All right. Now this is the question. If A is equal to AP1 plus BQ2, okay, and B is equal to CQ1 plus DP2. Find the value of the Poisson bracket A comma B. Right? We are dealing with Poisson bracket. Now we can easily solve this by using the properties of Poisson bracket that we discussed in one of the previous classes. So this is simply the Poisson bracket of A with B is equal to, let's write it down, AP1 plus BQ2, comma, CQ1 plus DP2. All right. Now we can expand this using the distributive law, or we can just take the non-zero contributions. Okay. If with some practice, you can identify the non-zero contribution just by practice. So if you look at this, you see that AP1 with CQ1, P1 with Q1 is non-zero. P1 with P2 is 0, so we don't have to write this, right? And the constants you can pull out of the Poisson bracket. So this is equal to AC P1 with Q1, am I right? From this term, AP1 with this term, plus, now we look at the second term, BQ2 with CQ1, that's 0, because Q2 with Q1 is 0. Q2 with P2 is non-zero. So this is, you can also pull out the constants, BD Q2 comma P2. Okay, so this is equal to P1 with Q1, right? That's equal to -1, that's equal to minus AC plus BD, because Q2 with P2 is 1. Okay, so the answer is BD minus AC. Okay, such simple questions also can be asked. Okay. So the properties that I've used here is this: QI with QJ is equal to 0. Pi with Pj is equal to 0, and Qi with Pj is equal to delta Ij. Okay. Also, we use the idea that this is antisymmetric, which means that Pj with Qi is equal to minus delta Ji. All right. So that's a simple one. Let's go into the next one. Is this okay? So I think someone is new here today.
Yes, sir.
All right. Here's a slightly more involved one. We're given the Lagrangian L equal to half ml square theta dot square minus mgl 1 minus cos theta. Okay. The Lagrangian is given. Right now, you are asked to find theta with theta dot. You are asked to find theta dot theta dot. Okay. Now we know the relations between Q and P. Right. So we have to write theta dot in terms of P. All right. Now there are different ways to write this. If the Hamiltonian is given, okay, sometimes in a problem they may give you the Hamiltonian. In that case, you can find, for example, Q dot by simply Q dot equal to dou H by dou P, right? Or Qi dot equal to dou H by dou Pi. But here we know the relation between the Lagrangian and the corresponding momentum. So we know that if the Lagrangian is given, sometimes this may be convenient. Okay, P theta is equal to dou L by dou theta dot. Okay, that's equal to ml square theta dot. Okay, so this means that theta dot is equal to P theta divided by ml square. Right. So theta with theta dot is P theta. This is correct, isn't it? Theta dot equal to, yeah. So theta with theta dot is equal to theta with P theta divided by ml square. Okay, that's equal to, you can pull the constant outside, 1 by ml square, theta with P theta, and that's equal to theta with P theta is 1. Okay, this is simply 1 by ml square. So theta with theta dot, the Poisson bracket is 1 divided by ml square. Okay, all right. So that's also is not particularly difficult once you know what to do. Okay.
ഒരു സംശയം ചോദിക്കട്ടെ?
ചോദിച്ചോളൂ.
ആ തീറ്റ പി തീറ്റ നമ്മള് അപ്പൊ അവിടെ ഒരു IH ക്രോസ് നമ്മൾ ഓപ്പറേറ്റർ ആയിട്ട് ചേഞ്ച് ചെയ്യുന്നുണ്ടോ? ഇല്ലല്ലോ.
ഇല്ല, ഇത് ക്ലാസിക്കൽ മെക്കാനിക്സ് ആണ്.
ക്വാണ്ടം മെക്കാനിക്സിലാണ് നമ്മളത് IH ക്രോസ്. അല്ല, ക്ലാസിക്കൽ മെക്കാനിക്സ് തന്നെ അത് പിന്നെ തീറ്റ തീറ്റ ഡോട്ട് മൈനസ് അല്ല, അത് എങ്ങനെയാണ് അതിന്റെ വർക്ക്ഔട്ട് എന്നുള്ളത്?
അതെ, so the rules obeyed by commutator and Poisson bracket are exactly the same. Okay. Except for the fundamental thing, this is different. Okay. Qi with Pj is equal to delta Ij. Delta Ij means if I is equal to j, this is 1. If I is not equal to j, this is equal to 0. Okay. This in classical mechanics. In quantum mechanics, you will have operators and you will have IH cross delta Ij.
Okay.
Here, this is the Poisson bracket and this is the commutator in quantum mechanics.
Okay.
But the properties that both commutator and what is a Poisson bracket follow the same properties. All right, I have given a few relations in the notes. I will resend the notes. Okay, and all those relations are the same for commutator and Poisson brackets. There's a deep similarity between them. So in fact, they are both Lie algebra. It's called Lie algebra, but we don't need those details. And this makes it easier to go from classical mechanics to quantum mechanics. So now we are doing classical mechanics. So we'll be using this relation Qi with Pj. This is a fundamental, all right? Fundamental thing, delta Ij. You can take this as a definition, or you can find it from the fundamental Poisson brackets, all right, by taking derivatives. It's good to take this as the definition, all right? You can just postulate this and the other properties of Poisson brackets and then get the whole classical mechanics from it. Okay, so sometimes it's easier not to use the derivative thing. We know that u with v, Poisson bracket, this is equal to dou u by dou qi, dou v by dou pi minus dou u by dou pi, dou v by dou qi. Am I right? Okay. So here again I am using summation convention. I is repeated, so it's understood that there's a summation over I. All right, we don't write it explicitly. It's known as Einstein summation convention. Okay, so that makes it simpler. All right, is that okay? Yes,
Okay.
Here is one more problem. In the same way, okay, L is equal to half m x dot square plus y dot square plus z dot square plus qb divided by 2 x y dot minus y x dot. Okay, so we are asked to find x dot with y dot, x dot with y dot. Okay, so in order to find x dot with y dot, we don't know the direct relation. Again, if the Hamiltonian is given, right, instead of the Lagrangian, if the Hamiltonian is given, you can find x dot by this thing, x dot equal to dou h by dou px, etc. All right, and then you'll get x dot in terms of px, and you can easily solve this. Here the Lagrangian is given, so let's find x dot, the relation between x dot and px. So we know that px equal to dou L by dou x dot. It's known as the conjugate momentum. Dou L by dou x dot, that's equal to, you take the derivative with respect to x dot, so that is mx dot, right? And here also there's an x dot. This is what is the velocity dependent potential, so mx dot minus, all right, because there's an x dot there, so qb divided by 2y. Okay, mx dot minus qb by 2y. Is that correct? Okay, so from here you see that we need x dot, right? So let's just solve this for x dot. Mx dot equal to px plus qb by 2y, all right, or x dot is equal to px plus qb by 2y divided by m. Similarly, we need to find y dot. Y dot. So we look for py is equal to dou L by dou y dot. And in that case, that's equal to my dot. Here it's plus QB by 2. Okay, what do we have there? X. All right. So you see that y dot equal to Py minus QB by 2 X divided by M. Okay. Now we have got X dot and Y dot. We just have to find X dot with Y dot. So now so X dot with Y dot is equal to Px. All right. So we can pull this M outside. It's a constant inside the Poisson bracket. You can pull it outside. So this is 1 by M square, right? Because there's constant in both terms. You can pull it out of the Poisson bracket. We have given this as a property of the Poisson bracket. So it's 1 by M square Px plus QB by 2y, comma, Py minus QB by 2 X. Again, you need to take only the non-zero terms here. So it's equal to 1 by M square. So you have got a Px here. The only non-zero combination is this. Okay, Px with Py is 0. So Px with that is the only non-zero combination. All right. So let's take the commutator right away because it's easy. Okay. All right. So 1 by M square. So Px with this term, that QB by 2 minus QB by 2 is a constant. You can take it outside of the Poisson bracket. What you have is Px with X, right? The Poisson bracket of Px with X, and that's equal to minus 1. Okay, we can skip some steps here. Plus, here again, you can take this QB by 2 outside, and the only non-zero thing is this thing, y with Py. Y with Py is just 1. Okay, I hope that's clear. So this is equal to 1 by M square. This is QB plus QB, right? Divided by 2. So that's simply QB. So the answer is QB divided by M square. Okay. The Poisson bracket X dot with Y dot is simply QB divided by M square. All right. Okay. Here's another one. Evaluate A dot R, comma, P vector. Okay, you're asked to find the Poisson bracket of A dot R with P. Okay, so A is said that it's constant vector. Okay, what we mean by constant vector is that its coefficients are constants. All right, so usually a vector can be written as, let's say some vector can be written as, all right. So for example, A vector can be something like this, 2i plus 3j plus k, for example. Okay, this is a constant vector because the components are constants. Okay, whereas R vector is equal to xi plus yj plus zk. These are not constants. Okay, so this is given. A is a constant vector. All right. Now, if you are given such problems, okay, it's better to work in component form. You've got a vector here. You've got a vector. So we'll take just one component of this vector and find the commutator, so the Poisson bracket. Okay. All right. And this is A vector dot R vector. So A vector dot R vector. So looking here, A dot R is equal to 2x plus 3y plus z, something like that, right? But so generally we can write this as A vector dot R vector is equal to A1 R1 plus A2 R2 plus A3 R3. Okay, where 1 stands for the x component, 2 for the y, and 3 for z component. Or generally, we can write this as AIRI. Okay, AIRI. Again, I am using the Einstein summation convention. I is repeated, so you have to understand that there is a sum over I. So the sum over I is understood. Right? Now we can write it down. Let's take, this is AIRI. Okay, let's take just one component. Okay, let's take A dot R with one component of P vector. Okay. So AI, Ri, comma Pj. Okay. Notice that I'm using I as a dummy index here, so I cannot use the same index there. You shouldn't. You cannot use the same index for different purposes. Okay. Here I is the dummy index. This I means that you have to sum over this I. Okay. So you'll have to use a different index there. Don't use I. Now this is equal to. This is easy because we know that this AI are constants, so simply Ri with Pj. Okay. This is AI. Ri with Pj is delta Ij. All right. It's delta Ij. And that's equal to simply Aj. Okay. Because the sum, there's a sum over I, and this delta Ij tells us that this is non-zero only for I equal to j. All right. In the whole summation, this is non-zero only for I equal to j. So we have got this result. A dot R with Pj is simply the corresponding jth component of A. So we can find the other components and show that with P vector. Okay. So you have got a j component here, you got a j here. So this has to be A vector. Okay, that's the answer. A dot R with P is equal to A vector. Okay. So another one, such questions are asked, okay, for competitive exams. A dot R, comma R vector. Okay, what's A dot R, comma R vector? Again, we can do the same steps. Okay, if you are familiar with this, you can say immediately that this is 0 because A is a constant vector and R is 0. So R with R is 0. But we can write one more step. This is equal to, or the, let's take the, again, the jth component. This is equal to AI Ri with Rj. Okay, the jth component of this with Rj. Okay, is equal to, and this is equal to AI Ri with Rj. So Ri means it's the ith component of R vector. Okay, if I is equal to 1, R1 is X, etc. So this is equal to 0. Okay. All right. Now we are going to next problem. We are asked to find A vector dot R vector square, comma, P vector. Okay. All right. So this is A dot R square. All right. Now this means A dot R multiplied by A dot R. Okay, you can do it in different ways, but I think we can again write it in index notation because A dot R is, we can say AI Ri. Okay, sum over I, AI Ri. That sum is understood side on right. Now you have to square it, so that's equal to AJ Rj. All right. So A dot R square. Let me just. So again, let's take the jth component here. So let's say A dot R square, comma Pj. Okay. So this is equal to, we can write it as A dot R square is A dot R multiplied by A dot R. Okay. And what's A dot R? It's a sum AI, Ri. And here I shouldn't use the same index. I use AJ, Rj. Okay. Sum over I and J are implied. All right. So this is equal to AI, Ri, AJ, Rj. So I shouldn't use J here. Okay. Because I used J as a dummy index there. Okay. Comma P, K. Let me use K as the next dummy, next index. Okay. So this AI and AJ are constants. I can pull it out. AI, AJ, Ri, Rj with Pk. All right. Now I'll just elaborate this. This is AI, AJ. Okay. Now this commutator, we can expand this is equal to Ri, not commutator, Poisson bracket. I'm sorry. Ri, Rj with Pk. Okay, you have to take both combinations, right? Plus Ri with Pk multiplied by Rj. All right, we had seen this property. UV with W, etc. Right? So the idea is that you will have to take both combinations, Ri with Pk, and then Rj will be left out. That's outside. Okay. Then you have to take Rj with Pk, then Ri will be left outside. Okay. And again, in classical mechanics, this order is not important. So it doesn't matter if you put this Rj here, no problem. In quantum mechanics, you should be very careful.
property
Okay, the property. This is uv with w. Okay, this is a product of two functions. This can be written as, first you take u with w, okay, and then multiplied by v. You can take v outside. It's just like the product rule. Okay, in fact, you can prove this using the product rule. Plus, now you have to take v with w. Okay, so that is v with w, and you have got a u outside. Okay. Now this is same for commutator also. This is true for commutator also. Okay, but for commutator, it's important that if v is in the second position, if v is on the right side of u, you have to put v here. If u is on the left side of v, you have to put u on the left side. Okay. In Poisson bracket, in classical mechanics, we can also write this as vuw plus uvw. Doesn't matter. The order does not matter. Okay. Is this clear?
Yes, sir.
Okay. Now this is equal to AIAJ RI, RJ with PK is delta JK. Okay. RI. So this is delta JK. Okay. RJ with PK is delta plus you've got an RJ there, and this is delta IK. Okay. Delta IK. Okay. That's the fundamental Poisson bracket. It is known as a Kronecker delta. Now this we can AI, AJ, RI, delta JK plus AI, AJ, RJ, delta IK. So now if you see these are all summations, okay? You have got AJ delta JK. But in this summation, there's a sum over J. In this summation, only one term will survive where J equal to K. So this term we can write as AI, AK, Ri, all right, the summation still remains, plus here it's delta Ik, okay, so that's equal to Ak, because in this whole summation over I, only I equal to K will remain, so it's equal to Ak, Aj, Rj, okay. Now if you look at it, it's exactly the same thing, all right. If you are not convinced, I can write this like this. Now the convenience of writing this in components like this is that you can just change the order, no problem, in classical mechanics. Okay, so this is AIRI. Okay, that's, so you have got an AK there, AIRI. So there's a summation over AIR, summation over I. So this is simply A vector dot R vector plus you have got AJRJ. That's also, there's a sum over J, so that's also A vector dot R vector. Okay. Now, what is this result? This result was, we found A dot R square with PK, which just took one component. So this is equal to, these are the same. So 2AK, A vector dot R vector. All right. Now this was just one component. So if you take all the components, you will have all the three components. All right. If P equal to K equal to 1, you will have A1 here. P equal to, K equal to 2, you will have A2. K equal to 3, you will have A3. So you can write it in vector form. Square with PK is equal to 2A vector. Or you can write it like this. 2A vector dot R vector multiplied by A vector. Okay. All right. Now we can also get it easily from the previous result by using one of the properties, but it's good to practice it in this way. Okay, because earlier we had this. Okay, it's all right. We'll just do it like this. You can think of simpler ways to do this. Now, if you notice in all of these things, I'm not using the definition of Poisson bracket. I'm just using the properties and the fundamental Poisson bracket. This is all I need. Okay. qi with pj is equal to delta ij. Okay, I'm not using the derivative thing, dou qi, dou u by dou qi, dou u by dou pj, something like that. I'm not using it. I'm just using the properties and this fundamental Poisson bracket. Okay. Okay, now comes another one. These are nice problems for practicing. We have got a vector dot r vector with the angular momentum. Okay, with the angular momentum. All right. Now I'll do it this fully, but later on you will see that there's a trick to do such problem. Not a trick, there's a result that will help us write down the answer. But just for practice, let's do this. Okay, so this is equal to, let's take again, this is a vector here, let's just take one component of this. So this is a dot r, we can write as ai ri. Okay, ai ri, comma, so there's a sum over I. Let's take lk, just one component of this. All right. Okay. So this is equal to, again, you can write this as AI. You can pull AI outside. Okay, in all these problems, A vector is a constant vector. So this is AI Ri with Lk. Okay. Now what is Lk? All right. We know that L vector is equal to R vector cross P vector. Am I right? So one component, I told you that we can write one component of this using the Levi-Civita. Okay, so Lk can be written as epsilon k, and then you need two more index. Let's say L and M. These are summation index R, L, P, M. Okay, this is the Levi-Civita. I told you the properties of Levi-Civita and the cross product between two vectors. Any component of the cross product between two vectors can be written using the Levi-Civita. Okay, I told you the properties of Levi-Civita. If these are in cyclic permutation, it's equal to 1. If they are non-cyclic, it's -1. If any two indices are the same, it's equal to 0. So the possible values are 1, -1, and 0. Okay, it's completely antisymmetric, etc. So this I can write it as. എന്താണ് this is known as a Levi-Civita. Okay, so the property is this. Okay, the defining property is this: epsilon 1, 2, 3. Okay, equal to epsilon 2, 3, 1 equal to epsilon 3, 1, 2. This is equal to +1. Okay, these are cyclic permutations of 1, 2, 3. All right, is that clear? 1, 2, 3. So we define epsilon 1, 2, 3 as 1. That's enough actually. Then you know that you also use the property that is antisymmetric. If you interchange, it is antisymmetric. Antisymmetric means if you interchange any two indices, you'll get a -1. Okay, so this means that we know that epsilon 1, 2, 3 is equal to 1. So if you interchange just two indices, 2, 1, 3, that's equal to -1. Okay, and again I can interchange two indices. So epsilon 2, 3, 1 is equal to, again there will be an extra -1, so minus multiplied by minus is plus. Okay, that's why you got epsilon 2, 3, 1 equal to +1. And similarly, you will see that you can get epsilon 3, 1, 2 by two changes from epsilon 1, 2, 3, or two changes from epsilon 2, 3, 1. All right. So similarly, if you make one more change, epsilon 3, 2, 1 is equal to -1 because an extra minus sign, and epsilon, if you can make one more interchange here between this, 3, 1, 2 again is equal to +1. This is how the property goes. Also, you will see that epsilon 2, 2, 3, for example, this is equal to 0. If any two indices are the same, this is equal to 0. Why? Because interchanging should give a minus sign, right? So you'll see that epsilon 2, 2, 3 is equal to minus epsilon 2, 2, 3. I have interchanged this 2 and 2. Okay, so something is equal to minus of itself, it has to be equal to 0. Right? So if you have a Levi-Civita and any two indices are the same, it's equal to 0. All right. The only non-zero terms are those for which all these indices are different. Okay. 1, 2, 3, all these things. And we know the minus sign is set. So whenever you make an interchange of two indices, you just add a minus sign. That's all. Okay. Is that all right?
Yes, sir.
It's defined like this. Okay, you can remember the definition. Epsilon 1, 2, 3 equal to 1. It's completely antisymmetric in all its indices. That's all you need to remember. Okay. This is equal to epsilon AI. Ri is there, and Lk is epsilon K Lm. Okay, I'm not using J because I'm using, okay, I'll use just L and M as dummy indices, and RL PM. Okay, and this epsilon, I told you these are constant, it's 1, 0, or minus 1, so you can again pull it out. So it's equal to AI epsilon K Lm Ri RL PM. Okay. So this is very convenient in solving problems. Okay. So this is AI epsilon K Lm, right? Okay, that's fine. This is Ri with RL PM. Let's take the non-zero term only. Ri with RL is 0. We don't have to worry about it. But Ri with PM is non-zero. So you take that combination, Ri with PM, and thus RL you have to put outside. Okay, using the property. Now this is equal to AI epsilon K Lm. Ri with PM is delta Im. Okay. And you have got Rn. So delta Im. Okay. So you can, so this means that there's a summation over I because I is repeated here, or we can consider it as summation over M. It doesn't matter. So let me just combine these terms. AI delta Im. Okay, in this summation, only one term will survive, one for which I equal to M. So this we can write it as Am epsilon K Lm. Okay. Because I've combined this AI delta M into Am. RL. Okay. Now I can write this as epsilon K Lm. There's no problem in shifting this around. So it is RL Am. Now what is this? By definition, I told you that R cos P. Okay, this is the kth component of R cos P. So this is equal to R cos A, the kth component of R cos A. Is this fine? Right? Because just using this definition, okay, R cos P, Lk is equal to epsilon K Lm R Lpm. So you just get it as R cos A, the kth component. Okay. But we were doing what? We were doing, this is equal to A dot R with Lk. Am I right? This is equal to R cos A. This is a vector and the kth component. Okay. So this means that A dot R with L vector. Okay. So if k equal to 1, you get the first component of R cos A. If k equal to 2, you get the second component. If k equal to 3, you get the third component. So this means that this is equal to R vector cross A vector. Okay. All right. Now, later you'll see that you may not have to do all these steps in order to get this result. Okay. But it's a good thing to practice. In case you don't remember some other result, you can always do this thing. Okay, just keep this result in mind. Okay, you see, this has to do with a particular peculiar property of the angular momentum vector. All right, the Poisson bracket with angular momentum vector has a peculiar property. I'll give that to you. Right, you just make a note of it. All right. Let's do one more angular momentum thing just to see the pattern. Okay, so this is the question. Evaluate A vector dot L vector with B vector dot L vector. Okay, A and B are constant vectors. All right. Now this we can write it as we have been doing so far. AI Li with Bj Lj. Okay, I and J are dummy indices. Summation over them is understood. Okay. So we can pull this out. AI Bj with Li with Lj, And in the previous class, we have already seen that Li with Lj is equal to, what is it? Epsilon I j k Lk. Am I right? Am I right? Yes. Okay. Li with Lj.
Yes,
This
sir.
result we derived in the last class. If you don't remember it, you can just take this as a result. Li with Lj is equal to epsilon I j k Lk. Okay. Now you don't have to derive the result. You can just think of this as the definition of angular momentum. All right. You can think of this as a definition of angular momentum. So that's equal to. So if I'm making a mistake, I may make a mistake by calling it commutator or calling it operator, etc., because of the hangover from quantum mechanics. But you understand that I'm talking only about classical mechanics, and we are dealing with Poisson brackets. Okay. So Aij epsilon ijk Lk. So let's write this like this: epsilon ijk. Okay. Ai bj Lk. What does that mean? What does that mean? Okay. So there are different ways in which we can write this using the property of this Levi-Civita. I can bring this k here, all right? So this is equal to, because I'm making two interchanges, there's no problem. We can do it without any extra minus sign. Okay, I'm taking k here first and then bringing it here. So two interchanges. So this is equal to epsilon kij, okay, ai bj lk. It depends on what options you are given, all right? So let me just, all right. Now what is epsilon kij aibj? This is equal to, as using the property of cross products, I told you that this is the kth component of A cross B, right? A cross B, okay? Kth component, right? This is how we define the cross product, the component of cross product using the Levi-Civita. And there is Lk. Okay. Now there's a summation over k. This means that you have to take each component of A cross B, the vector A cross B, multiplied by the same component of L and then add, which means that this is nothing but a scalar product. So this is A cross B dot L vector. Okay. So result A vector dot L vector, comma, B dot L. This is equal to A cross B L vector. Okay. What do you call this product? Cos and dot coming together. What do you call it? Okay, doesn't matter. But you know this property of this thing, right? Because if I have, this is kind of arbitrary. This is also equal to, let's just start from there. We have got epsilon k ij ai bj lk. Okay, it depends on how you wish to combine these terms. Okay, so I could also write this as epsilon k ij lk ai bj, right? And what is this now? Epsilon k ij. Sorry, that won't work. So let's write it in a way we are familiar with. We can write this also as epsilon ijk, right? We already had it, but let's write this because we can interchange this indices. Ai bj lk, right? Now if you take, this is equal to epsilon ijk, okay, bj lk, right? I'm combining these terms multiplied by ai. What is this now? What is this? This is the kth component of B cross L. Am I right? B cross L, kth component, sorry, ith component. I'm sorry, ith component. Okay. AI. So this is equal to B cross L dot A vector. That's also possible. Okay. That's a property of this cross product and dot appearing. You can take the cyclic permutations and get the same result, right? It's A cross B dot L is equal to, you know this property, right? A cross B dot L is equal to L cross A dot B. Okay, that's equal to, also you'll see that this is equal to B cross L A. Okay, all these are the same. And you can see this from the property of Levi-Civita. Okay, you know this result, I hope. So depending on what's given in your options, you should try to write it in that form. Okay. So one of these will be given in your options. Maybe one answer is given with a minus sign, because when you change the order of the cross product, you'll get a minus sign, etc. Okay. So that's done. All right. So there are more problems. Okay, let's do x with ly. Okay, and lx with y. Okay, these are two questions. You are being asked x with ly and lx with y. Okay. Should we do this, or I'll give you the result? I'll just give you the result. Okay, just follow the same steps. I'll put it in your notes. Okay, you'll see that. Okay, I'll tell you the steps. This x with ly, we can write x as r1. Okay, ly as L2. Okay, we are just using for x x is the first component of R or something. You can also write it as R1. Okay, Ly is the second component of L, so we write it as L2. Okay, now this you can write it as, okay, I'll just do this one. All right, R1. Okay, L2. What is L2? We know that Li is equal to, or we know that L vector is equal to R vector cross P vector Li. Okay, I, this is equal to epsilon I jk rj pk. Am I right? So here we can write this. This is R1 L2. L2 means if it's I here, you'll have an I there. So this is epsilon 2. Okay, and then you have two dummy index Lm RL Pm. Is that correct? That is L2. Right? You still have to sum over L and M, but many terms in that summation will be 0, but we don't worry about it now. This is equal to, you can take epsilon 2 Lm outside, R1 with RL Pm. Okay, take only the non-zero term now. Okay, this is R1 with Pm. Okay, and there's this RL there. So this is equal to epsilon 2 Lm. This is delta 1M RL. Okay, so summation over M here, the summation over M, and the only term that will survive is M equal to 1. So this is equal to epsilon 2L1. Okay, I'm just combining these two terms, RL. Okay, now there's a summation over L, but which is the only term that survives. Okay, we know that if any two indices are the same, then the Levi-Civita is 0. All right. So we have got 2 and 1 here. That's already fixed from the problem. So L has to be equal to 3. That's only non-zero term in this summation. So this is epsilon 231 R3. Okay. And epsilon 231 is plus 1. So this is simply equal to R3. And what is R3? R3 equal to Z. Right. R3 is the third component of R vector, and that's called also as Z. So we see that x with Ly is equal to Z. Okay, x with Ly is equal to Z. Okay. Make a mistake somewhere. Okay, I'll put it in the correct form in your notes. Okay, you have to check for the minus and you have to be careful. All right. But also you'll see that in the same way, you can see that Lx with y, Lx with y is equal to Z. Okay, you have to check this. I'll put it correctly. All right. Now, similarly, you can find Px with Ly or Px with Lz. Okay, or we can say P1 with Lz is equal to Pz. Right. You'll see that this result is also true. You can easily show this. Okay, I'm not doing all of them. I'll give you a result which is relevant here. The relevant result is this. Now you can, here onwards, you don't have to solve it completely. You can just use this result. The relevant result is this. If you have any vector that is associated to a system, which means that it's a function of x and p. Okay, for any vector, L has this property. Okay, suppose a vector is any. Let's call it a system vector. Okay, you remember this result. Let A vector be any system vector. Okay, system vector means its components are functions of x and p. All right, or it is defined in phase space, in other words. Okay, so then AI with LJ. Okay, this result always holds for all vectors. This is equal to epsilon ijk ak. Okay, this result is true for all vectors. Okay, this is very easy to remember, right? We already had this Li with Lj is equal to, okay, we know that L is component of vector, it acts like a vector. Actually, it's a pseudo vector, but that detail is not important here. So Ly with Lj, you use the same result because Li is a component of a vector, right? So you use the same result is epsilon I j k, and the kth component of this vector, right? You've got ak, so lk. This result we already had. Okay. Similarly, if you have pi with lj, okay, again p is a vector, so this is equal to epsilon I j k pk. This result always holds. All right. So you see that the angular momentum operator has some nice property on the vector, nice Poisson bracket property on the vector or on any system vector. Okay. You'll see that this is associated with a deep thing about the angular momentum. We'll see later that angular momentum is a generator of rotation. All right. Angular momentum operator. Soon we'll see in canonical transformations that this angular momentum operator is a generator of rotations, and we know how the vectors rotate, right? That's why this has the specific property on vectors. All right. So it's enough for you to remember this result, and you can easily apply it in the problems that you are doing. Okay. So let's check the previous result that we had. We had x with ly, right? X with ly. This we can write it as R1 with L2. Okay, R1 with L2. So by this result, this is equal to epsilon. If it is I here, you put I, J here, you put J here. So 1, 2, okay, and K, and RK. All right, is that correct? I'm just using this result. Okay, and what is this? You have a sum over K, but from the property of the Levi-Civita, there's only one term that's non-zero in this sum. All right, because we have fixed 1 and 2 here. The only non-zero term would be for k equal to 3. All right. If it's 1, 2, 1, it's 0. 1, 2, 2, it's 0. 1, 2, 3 is non-zero. That's 1. So this is equal to epsilon 1, 2, 3, k3, and epsilon 1, 2, 3 by definition, sorry, not k3, r3. Okay. By definition, we know that this is equal to r3, and that's equal to z. All right. So x with ly is z. I think we got it correct in the first place. Okay. So if it's any vector, we can just use this result. It's a shortcut. Okay. I think there will be one problem from Poisson bracket. Okay, sure thing. Or at least there will be a couple of problems that you can solve with Poisson bracket in an easy manner. All right. There are more problems here. We did all this. Okay, similarly, you can show that. Okay, this is easy. Okay, it's exactly the same steps that I've been doing. This is equal to a vector cross r vector. Okay, you can see that this is equal to a vector cross r vector. You just again use the same properties using Levi-Civita and all that. Okay. All right, then now this was asked for one of previous net or gate, I don't remember. X prime equal to x cos theta minus px sin theta. Okay, and px prime, this is some sort of a transformation, coordinate transformation. X sin theta plus px cos theta. All right, you are asked to find x prime with px prime. X prime with px prime. All right, the new coordinate and new momentum. This is equal to, just take the non-zero terms. All right, the first term, x cos theta with x sin theta, that's 0 because x with x is 0. X with px is non-zero. So you'll have x px and you have a cos theta and cos theta here. So it would be cos square theta plus, let's put minus. You've got sine, the only non-zero term would be px with x because px with px is 0. So minus, this minus is the sine theta you can pull outside. So sine square theta because the sine theta and sine theta, okay? That's equal to px with x, okay? X with px is 1. So this is cos square theta. Px with x is minus 1. So plus sine square theta. And the answer is 1. Okay. So x prime and px prime are also good candidates for coordinate and momenta because they obey the fundamental Poisson bracket relation. Okay. So in your notes, I'll put in a couple of more problems of the same form. Okay. Let's do just one more problem and okay, there are many problems here. Let's do this. The Hamiltonian is given. Okay, this could be given for any system. H equal to px square by 2m plus kx square. All right, it could be half kx square. Let's put half kx square. Okay, now the question is this: what is x dot with px dot? X dot with px dot. Okay, now we know that x dot equal to x with h, the Poisson bracket of x with h, right? So this is equal to, you take only the non-zero term here, okay? X with px square divided by 2m, okay, that's equal to 1 by 2m x with px square, and we already saw that the results of this. I'll just make it quick. We have seen results of this sort. Okay, that's equal to 1 by 2m. We got 2px, x with px. All right, you can say that. You can do this, okay? X with px into px plus x with px into px. That's 2 px, x with px. Okay, so that's equal to simply px divided by m. Why? Because x with px is 1. All right, and what's px dot? Px dot is equal to px with h, the Poisson bracket of px with h. And what's that? Okay, the only non-zero term is there, so that's equal to px with h. Okay, px with px is 0, so only non-zero term is there. I'll just pull this half k outside, half k, and you'll have px with x square. Am I right? I'm just making it quick. So it's equal to half k. What is px with x square? That's 2x multiplied by px with x. You just use the property of the Poisson bracket and you'll see that this is true. Okay. What is this? That's equal to minus kx, right? Because px with x is minus 1. So it's equal to minus kx. Minus kx. What do we have to find? We need to find x dot with px dot. We have got x dot and px dot. X dot is px by m. So x dot with px dot equal to px by m, comma x dot with px dot, right? So it's minus kx. Okay, again you pull the constants outside, minus k by m, px with x. Am I right? And px with x is minus 1, right? Px with x is, answer is k divided by m. All right, x dot with px dot is k by m. Such questions can be asked. All right, I'll do one more problem and stop. If you have any doubt, you can ask. All right, these are just straightforward steps. If you don't completely follow steps here, you can find it in the notes. There are many problems, so we have to make it rather quick sometimes. I hope you're following. Okay, it's not very difficult. Now this is another problem that was all right. So this was another problem that was given. H is equal to, we have solved this problem in a different way. Okay? h is equal to p theta square divided by 2ml square plus mgl1 minus cos theta. All right. The question is this: if L is the Lagrangian, if L is the Lagrangian, what is dl by dt? Okay, if L is the Lagrangian, what is dl by dt? Now we know that for any function f of the system, for any function f of q comma p comma t, okay, df by dt is equal to, we know this result, this is a fundamental result, df by dt equal to f comma h plus dou f by dou t. Okay, this is now if f has no explicit dependence on time, then this term is 0. If f has no explicit dependence on time, then this term is 0. So you can write df by dt is simply equal to f divided by h. Okay, so if f has no explicit dependence on time. In this case, you need to find dl by dt. We know that L has no explicit dependence on time. How do we know that? Because the Hamiltonian has no explicit dependence on time. Okay, we have this result. Okay, so if you remember from the previous class, we have this result: dou h by dou t equal to minus dou L by dou t. If h has no explicit dependence on time, then L has no explicit dependence on time. Okay, so that was just said. So we start with this. We know that dl by dt is L with h. That's all. Okay, dl by dt is L with h. Now we need to find L. Am I right? We need to find L. We know that L is equal to, okay, PIQI dot minus h. Okay, where there's a summation over I. In this case, there's only one coordinate, theta. Okay, so in our case, so L is, this is definition. Okay, let's say definition. Right. Now we can use this. We have only one coordinate, theta. So this is equal to P theta theta dot minus h minus mgl 1 minus cos theta. Okay, P theta theta dot. Now we need to find theta dot. All right. Now we need to find theta dot. What's theta dot? Theta dot equal to theta with h. Am I right? That's equal to theta with h. All right. This is Lagrange. Now let's just find theta dot. Theta dot equal to theta with h. Right? By definition, we have this result. Now there is a theta term here, that's 0. So that's equal to theta with p theta square by 2ml square. Okay, because other term is 0. So this is 1 by 2ml square. Theta with p theta square is 2p theta. Theta with p theta. Okay, that result we are using from previous thing, or we can just try. You'll see that this is true. So theta with p theta is 1, right? So this is equal to p theta divided by ml square. Okay, theta dot is p theta divided by ml square. So what do we have for the Lagrangian? L equal to p theta square divided by ml square minus p theta square by 2ml square minus mgl 1 minus cos theta. Okay, so you can just combine these terms. So it's simply p theta square divided by 2ml square, right? If you take the difference, you'll see that L is equal to p theta square divided by 2ml square minus mgl 1 minus cos theta. Okay. Did I make mistakes on p theta? I think that's correct. Yeah. Okay. Now we are ready to find L with, oh, actually we didn't have to do this. Okay, we didn't have to do the whole thing. Okay. Okay, there's an easier way to do this. Right? This is also correct, but there's an easier way to do this. We can write this simply as h. Okay, p theta theta dot minus h. That's equal to P theta, we already found theta dot. We don't have to expand h. I'll tell you why. Okay. P theta, theta dot. Theta dot is, so this P theta squared by ml square minus h. Okay, I'll maintain h at as itself. Okay, you'll see why in a moment. Right, is this clear? What I do is I take the definition of L, that's equal to P theta, theta dot minus h. Okay, and theta dot I already found is P theta by ml square. All right, so I substitute it here. So it's P theta square minus by ml square minus h. Okay, now we need to find L with h. That's equal to P theta square by ml square. Okay, minus h comma h. Okay, now we have two terms there, but one term is identically 0. You know that because h with h is equal to 0. All right, so that's the convenience of writing h as itself. H with h is 0. So your L with h now becomes simply P theta square divided by ml square comma h. Okay, because this term is 0. Okay, now we can write h, but you don't have to write all of h. Okay, there's only one non-zero term. Okay, P theta. So what is h? H is equal to P theta square by 2ml square plus mgl 1 minus cos theta. But the first term committed, so the Poisson bracket is 0. So you have only one term here, plus, comma, plus mgl 1 minus cos theta. You can pull this mgl divided by ml square outside. P theta with 1 minus cos theta. Okay, so that's equal to G divided by L. Okay, P theta. So this P theta with 1 is 0. With any constant, the Poisson bracket is 0. So equal to minus G by L. P theta with cos theta. I pulled also the minus sign outside. Okay. Okay, let's write it, or we can write it as G by L cos theta with P theta. Okay, this is easier. We just interchange this and we get one side. Now, what's cos theta with P theta? Okay. Now it seems that you cannot solve it immediately, but we have a nice result. We have got this nice result. You have to use this sometime, right? If you have some function, okay, with P, that's simply equal to, let's say this simply equal to dou F by dou Q. You remember this result, right? If you have some function of Q and P with P, that's equal to dou F by dou Q. So the Poisson bracket with P is simply the derivative with respect to theta. So it's equal to G by L dou by dou theta of cos theta. Okay, and divided theta of cos theta equal to minus sin theta. So it's equal to minus G by L sin theta. Okay, I think that's the final answer. Oh, no. There's a P theta square here, right? I'm sorry. Oh, so there will be 2 P theta here. Okay, I missed that square. So that square will give you 2 P theta there. I'm sorry for this. So you'll have a 2 P theta extra here. That's all. Okay, so the final answer is this. So it's equal to minus 2G by L P theta sin theta. Okay, I'm sorry, I dropped the square there. All right, so you just use the square also. So if you have a square here, it's simply 2 P theta multiplied by P theta with cos theta. So there's an extra 2 P theta over there. Right? So this is simply another way of solving the same problem. And I think this might be quicker. Right? If you are really familiar with these results, this way might be quicker than the previous thing that we did. Okay. All right. I think we'll wind up for today. If you have any questions, you can ask now. Anything? Any doubts?
No. Okay. Thank you, sir.
All right. So we'll see you tomorrow.
Okay, thank you, sir. Thank you so much.